our incubator program, the Cyclotron Road. And the Cyclotron Road actually supports startup companies in their first 2 years. And we are really proud at Lawrence Berkeley Lab that we had two of the most innovative geothermal startups in our program. This is Fervo Energy and Sanskar Energy. Fervo Energy is widely recognized for its disruptive advancements in EGS, but Sanskar is a really interesting company too, because Sanskar Energy leveraged machine learning and big data to uncover hidden geothermal prospects. And they just have recently shown that with this artificial intelligence-based technologies, they are able to optimize resource development. So analyzing existing data from production, for example, and this is really unique, I would say, in the whole geothermal world, can really help to optimize the resource development.
Welcome to Geothermal Unleashed, where we will explore the cutting edge of geothermal energy. I'm Elizabeth Cambre from the Vallourec New Energies team. I'm here to help educate and document geothermal's rise in the global energy transition. Today, I'm delighted to welcome Dr. Eva Schill to the show. Dr. Schill is the Geothermal Systems Program Lead at the Lawrence Berkeley National Laboratory. We will be discussing her career journey, the importance of geothermal energy, and the innovative work being done at the Lawrence Berkeley National Lab, including advancements in enhanced geothermal systems and the use of AI in exploration. So welcome, Dr. Schill. So first, I want to ask, could you walk us through your career background and explain how you came to work at the Lawrence Berkeley National Lab? And then I'm really interested to learn about what led you to specialize in the geothermal field.
Yeah, good morning, and thank you for inviting me to this podcast. Yeah, I'm happy to talk, of course, about my career. I'm a geologist. I am German, and I'm here at Lawrence Berkeley Lab only since not even 1 year. I took over this program lead. Yeah, because there are a lot of exciting projects and developments ongoing here in the United States and also at Berkeley Lab. And yeah, to walk you a little bit through my career, I did a PhD in geophysics, and actually my PhD was on the late tectonic evolution of the Himalayan mountains. And you would wonder what this has to do with geothermal, but indeed, because of this evolution, there was a formation of a number of hot springs in the Himalayan mountains, and this was actually my first contact with geothermal energy. Yeah, I actually quickly became passionate about this, and during my career, I became then the first junior professor for geothermal energy in Germany, and 1 year later, also the first professor for geothermal energy in Switzerland. I worked a lot in enhanced geothermal systems development, mostly also in the European EGS reference site, which is located in France. And over the past 10 years, I led the geoenergy division at the Karlsruhe Institute of Technology in Germany, where I was responsible for implementing large geoscientific research infrastructures. This includes developing a geothermal underground research laboratory, which is still under construction today. And also a research well on our campus for heat storage. Yeah, this was basically my career in a nutshell before coming to Lawrence Berkeley Lab. And joining the lab gave me really the opportunity to be part of the ongoing technological breakthrough in EGS in the US. And just to give you a little idea of what is this breakthrough about and why the development is different from what we had in Europe. Actually, Europe was leading for a long time the EGS development worldwide. And the concept at the time was really to try to improve permeability, to improve the reservoir quality by hydro-shearing existing fractures. And this was also very successful. It led to a number of EGS installations in Europe. However, it is still linked to existing permeability. And the really interesting development in the United States now is that we are looking really to create reservoirs, and so national labs, academia, and industry in a kind of joint effort, if you want to call it like this, really manage to advance hydraulic fracturing in crystalline basement rock in a way that we could basically successfully complete a trajectory that began with the Fenton Hill project at the Los Alamos lab in the 1970s, and bring it to a successful technology today. And maybe another word why I really wanted to join Berkeley Lab and not any other institution is that Berkeley Lab gives you the opportunity to do large-scale team science. And I think this is a crucial point for success in these technologies.
It's really interesting. I wasn't aware about the work that Europe was doing on EGS. That's really interesting to hear that component. So let's look at geothermal in the US. From your viewpoint, why should the United States focus on geothermal energy as a leading source of domestic energy?
Yeah, it is really this breakthrough I spoke about. So to be able to create reservoirs, this is not something which is a small technology. This allows us to basically be able to deploy EGS everywhere in the United States. So we are not anymore linked to natural resources or natural permeability. We are today able to create our own permeability, and the heat is basically everywhere. You just have to go maybe in the eastern part of the United States, you have to drill a little bit deeper to get the same temperatures. But heat is everywhere in the subsurface. So what we did not have so far is a technology that allows us to harvest this heat. So with the recent technological breakthroughs, the previously estimated potential capacity of EGS, which was rated to about 5,500 gigawatt electric, is kind of becoming a more realistic target. So I think we can really, by upscaling EGS, we can really make an important contribution to the electricity or also heat production in the United States. On the other hand, so geothermal energy also offers multiple strategic benefits to the United States. So electricity, heat, but we also get access to critical minerals. So one of our biggest projects today is ongoing in the Salton Sea, where we are looking into the lithium concentrations in the geothermal brine, and we are trying to develop concepts and technologies how to harvest these critical minerals. And moreover, we also have a synergy between oil and gas technology, which is is broadly distributed over the United States. And this oil and gas technologies, which we already have in place, enables us also to have access to already trained labor and to existing infrastructures like drill rigs. Yeah, if you look into the market, for example, in Europe, that's a big problem. Europe does not have this oil and gas industry, so they have a limited number of drill rigs, a limited number of labor in this kind of technology. So this is a big advantage in the United States. So I think we should really benefit from this. And last but not least, of course, the general advantages of geothermal energy. It provides reliable baseload power, and it goes along with a massive subsurface storage capacity, which we very often forget. But this is a kind of another. It's not EGS, but it's another technology which we can really largely benefit from.
Wonderful. So before we get too much further into our discussion, which is going to continue to include EGS or enhanced geothermal systems, I want to pause and just make sure our listeners know what EGS is. Geothermal Unleashed listeners are growing rapidly each and every week, and we have got listeners who are outside of this field. So can you take out of the geothermal field, can you take a moment and explain the difference between conventional geothermal systems and enhanced geothermal systems?
Yeah, sure. So let's start from the conventional geothermal system. So maybe some of your listeners know about the geysers in Northern California, or I just mentioned the Salton Sea region in Southern California. So conventional geothermal systems basically take advantage of naturally existing reservoirs, geothermal reservoirs. So we have either hot water, or in the case of the geysers, even steam in the subsurface. So these conventional geothermal systems typically have high temperature and a high enthalpy geothermal fluids. You can find them, especially in the Western United States, and they often have surface manifestations such as hot springs or fumaroles along with the reservoir at depths. Their occurrence, however, is limited to kind of tectonically active areas, such as we have here in the Western US. So again, that's why this EGS technology is so important. So EGS, enhanced geothermal systems, as the name already implies, requires an active enhancement or active engineering of the subsurface to create or to improve fracture networks in the subsurface. These reservoirs that do not occur enough or that do not produce enough flow without intervention need a kind of treatment to basically create them or improve them. They are found mostly in the crystalline basement, like in granitic rock, and yeah, their natural characteristic is that they do not produce sufficient fluid flow in order to harvest the heat. As I said already before, for many years the focus was on enhancing permeability of existing fractured reservoirs, and the true breakthrough now came with the ability to create entirely new fractured reservoirs. And this advancement is significant. It enables the technology to become also truly scalable. So we can basically, from the point where we started now in Utah, we can upscale the technology and bring it across the United States.
Okay, so before we connected, I will admit I was not aware that the Lawrence Berkeley National Lab was so dedicated to developing technologies for EGS. So this was quite exciting for me when we connected to learn this. So I want to ask, and I just want to maybe we can stress the point, why is the Lawrence Berkeley National Laboratory putting so much emphasis on EGS in the US in particular?
So maybe first and foremost, it is scientifically fascinating.
Okay.
So we are a science lab, and we really love to work in this technology because it holds still so many unknowns. So we have a breakthrough, but there are still many open questions, and yeah, they are fascinating for us. But so EGS basically represents the most disruptive technology advancement in the geoenergy sector since the development of unconventional hydrocarbon production. And this is another really exciting time for us as scientists to be part of this development. Berkeley Lab actually offers also several unique capabilities that positions us to make significant contributions to this field. So we bring over 40 years of experience in monitoring induced seismicity. And induced seismicity is a key factor in understanding and managing the reservoir development for EGS. So basically, we create these reservoirs, and the only possibility to image our reservoir is induced seismicity. So we do not see induced seismicity as a risk. We see it more as a tool really to understand our reservoir, and we are very experienced in doing this. At Berkeley Lab, we have developed tools and technologies also to measure aseismic deformation. This is the non-seismic part of the reservoir development. And if you want to have a picture of what aseismic deformation is, I think it can be considered as the dark matter of geothermal systems. So it's rarely measured, and it's also not so well understood. However, aseismic deformation plays a critical role in subsurface systems behavior, and especially also in the long-term integrity of the geothermal installations. So this is one of our research foci at the moment. Yes,
Can I
so
ask? I find this to be quite fascinating because I never thought that you could be looking at seismic data. I mean, I always thought induced seismicity was a risk, and now you're telling me that you can actually use this tool to better understand. And I never thought of that. So I find that to be very interesting. But can you help me understand a little bit better? So what type of information do you get then to understand about the geothermal formation from induced seismic activity that you're
yeah.
monitoring?
Yeah. So basically, what we get, so how we do this, so how we create a reservoir, we inject water from the well into the rock formation, and we basically break the rock, we open the rock, and uh, then of course as in the shale gas industry, we inject also proppants in order to keep this stable. So while we break the rock and while we move these cracks in the subsurface, uh, you can imagine that the rock before was intact. Then you open somewhere a fracture, you move this fracture, and there's a lot of friction. So the fracture does not want to move actually. So there's a lot of friction preventing this motion. And while you overcome this friction at these rough surfaces, this is the point where induced seismicity is created. And that helps us basically because we can locate the source of the seismicity very accurately. And whenever we know that there was an induced seismic event somewhere, we know that something in the subsurface moved. So this is basically the classical way of imaging the creation and the movement of fractures. And when we know where the fractures move, we also know how far our fluid, which we inject, travels in the subsurface. And this gives us a first hint of how big our fracture is, how big our reservoir is. So that is actually how we use induced seismicity in a positive way. I do not want to say that there is no risk associated with induced seismicity. I mean, we have worldwide, we had a number of examples where induced seismicity can also kind of become really problematic. There are not so many cases actually where we really have experienced damage, but there are, of course. But for us as scientists, as technical person, it's really more a tool to image the creation of the reservoir in the subsurface.
Thank you for that. Can we turn now to talk about the work that's being done at the Geysers in California? So my understanding is the Lawrence Berkeley National Lab has work where you're looking at technologies for temperatures that exceed 750 degrees Fahrenheit. That is hot. Can you touch on this?
Yeah, so this was actually a work which was, as many of our projects are, funded by the Department of Energy. And the Department of Energy already very early actually had this idea to develop EGS. Yeah, as I said before, so after the Los Alamos experiment where we tried to create already an artificial reservoir, the focus was more on kind of enhancing existing systems. So what happened in the geysers at that time was that 3 previously abandoned wells were successfully reopened, deepened, and completed for EGS operation. And the reason for why this was done in the geysers is that, of course, even in a conventional field, you always experience also failures during drilling. So you from time to time you also drill a dry well in a conventional field. So not every well is successful. And the idea behind this project was make these dry wells also available for production. Yeah, so actually, when these wells were deepened, temperatures reached up to 750 degrees Fahrenheit. And the objective of the project at the time was to establish an EGS by injecting cold water at relatively low flow rates of approximately 25 liters per second. And actually, the history behind these low flow rates is also an experience which we had in Europe, that if we inject at relatively low flow rates, we can mitigate the risky part of induced seismicity. Yeah, so the contribution of Berkeley Lab at the time was mostly reservoir modeling. So we have developed over decades modeling capacities and capabilities at the lab. And so we were able to build a model of this wells and the reservoir, and to basically couple thermal, hydraulic, and mechanical processes in this model. And the idea was to evaluate and to optimize this injection strategy during the reservoir creation. So maybe just to report something on the results, our modeling indicated that observed seismicity was primarily due to shear reactivation. That means, again, for the overall EGS development, it means and this is a general observation which we have also in other experiments, we do not create seismicity when we open the fractures, but we create seismicity when we move the fractures. So when we move the two sides of the fracture against each other. So this was a major outcome of this project. And so this shear activation of pre-existing fractures was triggered on the one hand, by thermal cooling, of course, by the injection of cold water into this very hot rock, um, and also by minor changes of steam pressure. So that's also what was also an interesting finding, that we could basically understand the source of the induced seismicity.
Okay, so let's talk now about the work that's being done at the Geoscience Measurement Facility. So let's talk about particularly the development of new technologies like fiber optic sensing tools and the GPS receivers. How will these advancements help accelerate EGS development?
Yeah, so maybe just to explain what the Geoscience Measurement Facility is. This is a particular facility at Lawrence Berkeley Lab, and it kind of so every I would say every lab has its workshop, but this facility really differs from kind of ordinary workshops, which we also have, of course, at Berkeley Lab. And we in this facility we really we have very, very skilled engineers, which are basically providing us a design to deployment instrumentation solutions. And that's really very interesting, because for us scientists, we come to the GMF and say, hey, I would like to do this experiment. I would need a tool that can do this and that measurement. And our engineers, they are really great. So they make a design, they discuss the design with us. We really work very closely together to create or to construct later the best tool for the specific experiment. Yeah, so yeah, it's really not something that you can buy from the shelf. They really design the instruments according to our needs, and this actually led to a lot of innovative tools which we designed and constructed at GMF. So we basically developed worldwide unique prototypes and analysis tools in this facility. Maybe just to give you an example, two of the most exciting current tools are related to measurement of deformation. And what I said before, that we are also able to work on aseismic deformation, this is really thanks to the development of these tools. These instruments allow us to measure the full deformation. And so what we can do is we can capture both seismic and aseismic components of the deformation. And it really brings us to the forefront of research. So in recent underground research experiments, they enabled us to pinpoint the specific deformation processes that lead to induced seismicity. And this again is an important step forward in understanding how such seismic events occur. And if we understand how they occur, at a certain point, we are also able to manage induced seismicity. So this is really the probably the next big challenge which we have, or where we are looking into, is how can we manage induced seismicity, which will be an important point if we think about upscaling EGS across the United States. So the effective management of induced seismicity at that point will be really critical. So I think that's how GMF can advance and accelerate EGS development.
Okay, so let's turn to Utah Forge. What technologies from the Lawrence Berkeley National Lab are currently being deployed at Forge?
Again, this is all, some of the tools, I have to say, not all. Some of the tools are, again, coming out of GMF. So in the most recent fracturing experiments, we monitored the fracture evolution. And again, this is really important to understand, that we do not only monitor induced seismicity, but we deployed distributed acoustic sensing cables for vertical seismic profiling. And to enable the monitoring of fracture evolution, we deployed also a permanent seismic source, which we call the surface orbital vibrator. And this surface orbital vibrator was entirely designed and constructed again at GMF. The interesting thing about this is that our observations reveal the presence of natural faults and fractures within the granite, which was, of course, we knew that there are some faults, but it was not totally clear what is the role of these existing fractures for the creation of the reservoir. And we were able to characterize these fractures by time-dependent changes in seismic reflectivity. So we basically observe with the dust cable, we observe not only induced seismicity but also the entire deformation. And this gives us then a picture of when fractures open and maybe also when they close again. Yeah, so the mapping and observation of structures in the granite using these active seismic shifts, these active seismic signals, they basically shift the paradigm in monitoring of fractures in EGS. So we can today really not only see when the seismicity occurs and where it occurs and then infer where the fracture is, but we can really look into the deformation of the fracture itself.
Okay. And then I assume you can take, with understanding if the fractures are open, where your fluid's going, you can then look at temperature and then maybe better understand like the temperature degradation of your geothermal resource. Is that?
Exactly. So if you want, so the fluid field or the hydraulic field and the temperature field are not necessarily always directly linked, but they are linked, of course. And it is especially important to understand where the fluid really goes and where are preferential fluid pathways, because you can imagine that if you have a very good fluid pathway, the flow is very fast, and so this also bears a risk of thermal breakthrough. So at the end, the water could be travel so fast from the injection to the production well that it is not able to take up enough heat. So these things are all important, yeah, and we have to understand those even better. And we are also working currently on new or different technologies in order to be able to catch the electric signal better. And the electric signal is a very, very good indicator for fluid flow. It has a bit of disadvantage that we cannot capture it in this high resolution as we do with the seismic signal. But still, we think it's worth to investigate this, and the electric signal could also actually capture temperature changes. So that's a really new development. So we really try to combine the two monitoring techniques.
That is exciting. The whole research on EGS and what the lab is doing is very exciting. I agree with that statement you made earlier. Can you share some details about the lab project that is called EGS Collab? So what are the differences between developing, monitoring, and stimulating an EGS well versus an oil and gas well?
Okay, yeah, so the collab actually is my favorite thing to talk about. So I could talk for hours. I will not do that. But the collab project was a multi-lab effort, I have to say. So many national labs were involved. It was led by Berkeley Lab, and the experiments were done at the surf mine in South Dakota. So the intention of EGS Collab was to prepare the DOE Forge project, which now we have installed in Utah. And I would say it was also kind of successful because we had three major fracturing experiments in the in the Collab project. And interestingly, the hydraulic fracturing, so the hydrofracking experiment was really the successful experiment. So we were successful in generating a connected fracture system in the crystalline basement rock. This was also a period, so it was in 2017. It was a period when a number of these experiments were done also in other underground labs. So this was really an important step forward in learning how we can manage and we can control fracture creation in the crystalline basement. And this basically already represents one of the fundamental differences between oil and gas fracturing and EGS. So in the shale, the fracturing highly depends, for example, on the carbonate or on the quartz content of the shale, because it controls basically if the shale deforms more ductile or if it deforms more brittle. The basement rock, at least at these temperatures, is clearly deforms in a brittle way. But the basement rock has different mechanical properties. And it also occurs at deeper in the subsurface, of course, and deeper means always higher temperatures, higher stress conditions. And what we observed both in the Forge project and especially also in the Fervo project is that in the basement rock, fractures have also a tendency to connect to natural fractures. We can learn a lot from shale gas fracturing, and a lot of technologies have been transferred, but we really have to adapt the technology to the new conditions. And again, if we talk about temperatures higher than 750 degrees Fahrenheit, then the rock starts to deform in a ductile way. So it's a kind of a semi-ductile condition. And this actually opens a whole new set of scientific questions, like how do we fracture this type of rock? And in this way, we can again go back to oil and gas, because shale, if it's a rather poor shale, it can also deform in a ductile way. So that we can, I would say, learn from each other. But on the other hand, it would be too risky to say we just use oil and gas technology and then everything will be fine. So we really have to adapt it to the geothermal conditions. But yes, we can really learn from each other a lot. And yeah, so in summary, the oil and gas technology is really interesting for us, and we learn a lot from them, but it does not solve all our challenges.
Okay, so my last question that I have for you is, what are some of the technologies being developed around the use of AI for exploration purposes? And how significant can AI be in selecting the right candidate?
Okay, I would, this offers me an opportunity which I would really like to take. And I would like to highlight our incubator program, the cyclotron node. And the cyclotron node actually supports startup companies in their first 2 years. And we are really proud at Lawrence Berkeley Lab that we had two of the most innovative geothermal startups in our program. This is Fervo Energy and Sanskar Energy. Fervo Energy is widely recognized for its disruptive advancements in EGS, but Sanskar is a really interesting company too, because Sanskar Energy leveraged machine learning and big data to uncover hidden geothermal prospects. And they just have recently shown that they, with this artificial intelligence based technologies, they are able to optimize resource development. So analyzing existing data from production, for example, and this is really unique, I would say, in the whole geothermal world, can really help to optimize the resource development. So AI is really a great tool, and also at Berkeley Lab we use machine learning, for example, to improve the interpretation of seismic data. So seismic measurements it's always huge data sets, and that's exactly what AI or machine learning tools are made for. So if we apply machine learning to seismic data, we can enhance our ability to image fracture networks, to understand subsurface processes in geothermal systems. And it really, I would really say we are at the beginning of this kind of development, but we have the potential to do much more, because we in earth sciences in general, but especially in seismics or other exploration technologies, we create data sets that basically ask for evaluation with AI and machine learning. So I think AI technologies can detect patterns in large complex data sets. And so these patterns we often miss if we just analyze them in a conventional way. And as our data volume grows, AI becomes an increasingly powerful tool, and we should really go forward with the application in geothermal technologies.
Yeah, it's very exciting to see the impact that AI could have on the geothermal space. Dr. Schill, I would like to thank you for joining us on this episode of Geothermal Unleashed. It's been a pleasure. I hope today's discussion has sparked new insights and deepened everyone's understanding of the geothermal industry's incredible potential. Until next time, keep pushing the boundaries of what's possible, and let's continue working together to unleash the full potential of geothermal. Thank you.